I'm Chris Brown, and this is the 6th module in a series on axiomatic design, which is part of a course on axiomatic design and manufacturing processes here at Worcester Polytechnic Institute, where I am a professor in the mechanical engineering department. So far we've gone through the axioms and some of the structure and the decompositions, and so this module is some examples of decompositions. We're going to start out with actually one of my favorites. This came from industry, where I was giving a special short course, which I get to do occasionally. So it's about centerless grinding. So this company had a part that needed to be centerless ground. And they're making a kind of tube that was used for orthopedic or arthroscopic surgery, often used by orthopedic surgeons. So the person who had been feeding this centerless grinder, and let's take a look at the centerless grinder here for a moment again. So the part is a cylinder, and that's the yellow thing, W, that gets turned around by a regulating wheel, R, and it's ground by the grinding wheel, and it's supported by the blade. And so it gets fed through this thing by a slight misalignment of the regulating wheel and the grinding wheel, so that it gets ground to just the right dimension all the way through. And it does it without having to put it on center. So this is a nice process, but in reality these wheels are spinning around, and it can look a little bit frightening to the person who has to load it. So the person who had been loading these parts in the machine had left the company, and there was nobody else that could really feed it properly that was available to do it. And so as the person's trying to feed it and sort of dropping the part in, they would be slightly misaligned, perhaps, and wouldn't be fed in properly, and then the part would jam, and the wheels would have to be reset, and they were seriously behind on filling orders. Now another thing is that this is used for cutting, and the sharp end was already cut in it, and that was the way it had to be processed. So this made it even more uncomfortable for the person who had to handle it. So when I was there, the engineers had imagined setting up a multi-axis robot which would essentially simulate the motion of the hand in feeding the part. And they said, well, we're going to select it and take a month to develop the programs and get that going. And they said, all right, so what can we do about this design? Well, it's a nice kind of design problem in manufacturing processes, part feeding. And so the first step is to develop the minimum number of FRs that are mutually exclusive and collectively exhaustive necessary to solve the problem. So see if you can list the FRs and the DPs at the top level. It's kind of an exercise. And so the FR0 is to feed the parts. All right, so now decompose that into first level FRs and see what you might have for the DPs. And you might want to turn off the video and try that. So here's what we came up with. FR1 was going to align the part prior to insertion, and then 2 is going to be maintain the alignment during insertion, and FR3 is to protect the operator from the sharp end. So, and then as we decompose FR1, that seemed to be align the part within the holder and then align the holder to the machine. So this seemed to be the minimum list that was collectively exhaustive and mutually exclusive that would add up to feed the part into the machine and satisfy the customer need. So the design parameters then, what do we need? Well, to align something, you need, to align a tube, you would need a couple of support points in the front and the back, and this could be supplied by a V, and then an appropriate bracket. The other thing is, look at DP2, all right, so there should be a slot, and so that would be a whole V block now to maintain the alignment during the insertion, and for DP3, put a little push block there so that the operator doesn't have to deal with the sharp end. So as we go to draw the thing, another way to do it. So an alternative list of functional requirements. restrict the motion to the z-axis at desired location in x and y, and then protect the operator from the sharp end. So if we go back here, you can see the z-axis is indicated trying to be in line with the part. So there's an alternative set, and it's and it comes up with essentially the same dp's, which is interesting because this means there's not one unique way to come up with the best design. There may be equivalent ways to coming up with the same thing. This one looks a little better because it only has 2 FRs, and so that would be a smaller number and therefore be desirable, but the solution ends up being the same. So here's what it would look like with a kind of sketch, which is the next thing you go to. There's the part in blue, and then the DPs with the numbers attached so that we can see what the intent was. So this was facilitated then by a clear statement of the FRs. A robot was not needed. It was kind of satisfying too, because as we looked at this, they'd been struggling with this and trying to select a robot and wanted to know how they should design this whole system. And the light sort of went on at one point as I got them to develop themselves what the FRs and the DPs were by just asking questions. Are we sure this is the minimum number? What do you really need to align something? How can you align a tube? And the lights went on. One of the guys left the room, came back about an hour later and said it's in production and it works. So, so the importance then of stating the FRs clearly and getting them to be collectively exhaustive, mutually exclusive, and minimum in number. So the production bottleneck was removed. So this gets at some of the themes of mechanical design. Position is one thing to be thinking about. Load transmission and motion control are typical kinds of themes that you might want to be developing in the design, in mechanical design. All right, let's take a look at another example. This is, as I mentioned in the introduction, I've spent some time ski racing and coaching skiing. And so the actual transmitting control loads is not a problem that's unique to skiing. In fact, in almost every kind of moving vehicle and every kind of machine tool where you have some motion, it's necessary to transmit control loads. If we zoom in on this, I mean, this one's a little bit more fun to look at maybe because we're moving quickly over snow. And the skier is controlled by the interaction of the edge of the ski with the surface of the snow. And so the skier needs to be able to manipulate that edge, particularly rolling it up on edge and further on edge and applying loads to it. So being able to transmit roll moments and apply loads are essential, forward and aft moments as well. So let's take a look and see how this goes. So the first shot, you might do a decomposition like this. Transmit forces at the upper level and transmit moments, 2 different kinds of loads. And so then we could do the decomposition logically in terms of Cartesian coordinates. So we get forces in the x, y, and z direction. And in order to do that, we would have the appropriate kinds of interfaces on the corresponding planes. Transmitting the moments, so now I want to transmit a moment about the x-axis, I need to be able to have a couple transmitting this. So I need a force and a lever arm, or force and a distance. And that's the reason for the R cross L there, to emphasize that we need a couple. So we might take a quick look at this too. This has been decomposed in Claro, which you can purchase from axiomaticdesign.com, ADSI. So, and that's available, you can find their website. All right, so if we look at the FRs, they're all stated in the imperative: transmit loads, transmit forces, transmit moments. Transmit seems to be an appropriate child of transmit. and what we're doing is decomposing the directions, and then to a certain extent transmitting moments and forces is a decomposition, of course, of transferring loads. And so there's, as I said, a clear theme, which is sort of Cartesian. And the moments transmitted through a couple, as we noted before. All right, so test for minimum number. So is this good? See me min. Now, if we take a look, if we decompose 2.1 further, we see, there's a lever arm and a force. Now, the transmit force looks very similar to the children of FR1, actually to FR1. So if we satisfy FR2 and are able to transfer all the forces for the moments, then we no longer need FR1, and just trying to do that would result in redundant structures. So, therefore, we can eliminate FR1, and all we have to do is transmit moments. Now, if we take a look, we have a single child decomposition of FR0. It's only got one child transmit moments. So we could elevate transmit moments to FR0. And so now we have a simpler design. So here's just a look at the kinds of mechanisms that are involved in a ski binding, and some examples from patents, even those patents that are going back 30 years or so, or more. The fundamentals of ski bindings have not changed significantly in some ways since then, particularly when it comes to moment transmission. We looked at this briefly in a previous module, and this is the jig grinder. Now, this was a WPI undergrad summer project from Saint-Gobain here in Worcester. And the customer need is to make precision holes in hard materials for tooling, fixtures, and precision components. So we need to provide high-speed rotation, slow-speed vertical reciprocal motion, and positioning in X, Y, and Z. So those are typical things for a machine tool. So there's the sort of the jigging motions, though, that's particular to jigging. So essentially what you have is a little abrasive cylinder with abrasive sort of glued onto or attached to some sort of metal. And then this is spinning around at a relatively high speed and then jigging up and down and positioned in X and Y. So you can buy these, of course, and Moore makes excellent jig grinders. But the desire at Saint-Gobain was to make an attachment to go on a Haas mini mill. And the Haas mini mill was going to supply the jigging motion, and then use a high-speed air spindle, and then attach the hold device to the Haas spindle, which wouldn't be turning. So you would get the high-speed rotation from the air spindle because the Haas spindle wasn't fast enough. So here's the Haas mini mill from that era when we were working on that. And so first we're going to develop the high-level FRs and the constraints from the customer needs, select the corresponding design parameters, check for coupling in violation of the constraints, and then go to the next level. So here's the 0 level and the first level for the decomposition, the FRs and the DPs. Now, so one of the things that changed as we did this is that the jigging motion, they found out, could not be supplied adequately by the Haas mini mill. It resulted, there's so much motion jigging up and down, not as intended for that era anyway of a milling machine. So now there's an FR5, which is provide the jigging motion to the high-speed spindle, and then you can see anyway. So we have 7 FRs and DP pairs, and some of these things at first at the high level seem to be a little bit simple, and that, for example, FR5 provide jigging motion to the high-speed spindle. DP is a jigging motion system. FR7 is to restrain the motion to the Z direction, right? Let's take a look at how this decomposes, FR7. And then we can look at the integrated solution. So in order to restrain the motion in the Z direction, we need some sort of we decided to go with a bearing and rail system, as it says here. So we can see that at the top of FR7. And so then we want to restrain rotation about Y. If we look at 7.1, 7.2, restrain rotation about X. And then 7.3, maintain the location. 7.4, provide rigid connections. And then connect the rail stiffly to the mill. And I can let you go down and see how those are all decomposed. This is so a typical sort of motion theme in Cartesian coordinates, and some of these actually could be worded better. So let me point out some critical analysis of this. This was done several years ago. Let's take a look at 7.1.1.3.1. The FR is provide a plate surface orientation, and the DP is a precision ground plate. So the FR here is anticipating the DP and doesn't really allow for any flexibility or choice in the design. Provide plate surface with the right orientation, and then a precision ground plate and a rail interface. So that looks like it's anticipating the DP, and it's not in a completely solution neutral environment. So anyway, we can critique some of these things. One of the remarkable things about this, though, was that it was a team of 2 undergraduates working on for the summer that were able to design and manufacture all these parts in WPI's Haas Technical Education Center. So here's the physical integration, which we looked at briefly before, and we can see the rails that are restricting the motion and the placement of the rails that restrict the rotation. And then we can see different components. Now, we haven't put them all on here because there are too many, but this shows some of the things, how it's restricted between these plates, for example, to provide the right orientation. So anyway, so here we can see the design intent. So here is a photograph of the actual device as it was being developed, and we can see the pneumatic tubes coming in to provide the jigging motion, the vertical jigging motion. Here it is actually mounted on a test on a machine at Saint-Gobain, the first prototype, and this actually worked satisfactorily. So that ends that series of examples, and the next module is going to be to take a closer look at Axiom 2. So far we've been concentrating on Axiom 1. I might add that there's a lot of low-hanging fruit, and people do well in design just concentrating on Axiom 1 by itself and getting rid of coupling. One of the remarkable things too about this jig device is that it essentially worked first try, because as they were going through, they were able to eliminate all the coupling, get rid of the unintended consequences, and then so this functioned as intended on the first attempt. So there's no need to iterate and come back and change something. So and it was done all over a summer recess. Well, thank you for your attention.